Good morning, ladies and gentlemen. First of all, I would like to thank you for the opportunity to present my paper with title Understanding the Impact of Formation Properties on Stress Shadow in Multistage Hydraulic Fracturing through Modeling and Simulation. My name is Agustinus Zandy. I'm working with UND. I'm working for UND EERC. This is the EERC disclaimer, and I'll start with the background. Unconventional plays require horizontal drilling and multi-stage hydraulic fracturing techniques for the extraction of oil or gas. But the stress shadows impact the hydraulic fracture effectiveness. We are talking about the geometry and also the orientation on this term. And the stress shadow development has been studied. It's known that the stress shadow controlled by the formation properties and also hydraulic fracturing parameters. But the relationship between the hydraulic fracturing spacing and also the stress shadow has not been established yet. That's why we are conducting this research to understand the relationship between the hydraulic fracture spacing and also the stress shadow. So what is the stress shadow? The stress shadow is a stress accumulation in the target zone that changes the principal stresses value. The stresses accumulation is caused by the development of the hydraulic fractures itself. I'll provide an illustration. This is the direction of the maximum horizontal stress, and this one is the direction of the minimum horizontal stress. Assume that the black lines is the casing, while the gap between the black lines represents the perforations with the spacing of x. When we perform the hydraulic fracturing job, the fractures propagate into the formation from this perforation. And then we do the second one, third one, and fourth one. So when we generate the first hydraulic fracture, it also creates the stress shadow shown in the red highlighted area. When the stress shadow overlays the next perforation, the next fracture grows shorter or affected by the stress shadow. So what does it impact? When we talk about the unconventional plays, SRV or stimulated reservoir volume is very critical. If we have this fracture with this geometry, so the simplified illustration, the SRV will look like this, which shown in a green area. So we will lose the opportunity to produce from this section because this is unstimulated. So what the objective? The objective is to develop a method for optimizing the hydraulic fracture spacing by understanding the relationship between hydraulic fracture parameters and also the formation properties, and also to determine the effect of stress shadow on hydraulic fracture geometry. So this is the proposed idea. Let's say we have this geometry. This is the old design. We have the fracture spacing of x with the maximum of 3x. And with this, we can optimize this one become y and also become 2y. It will look like this. How does it impact? If we can change this geometry, become this geometry, and then we can do every single stage, it means we will recover the missing area, which is from this section, and we can enhance the stimulated reservoir volume becomes like this. So what does it mean? It means we increase the recoverable reserve from one well or total oil from or total reserve from a well. So what methods we did? So first we built the base model, the 3-stage model and also the 5-stage model, and also did the sensitivity analysis for the formation properties and also the fracture properties, so we can understand the fracture propagation and also how it interacts between one to another. And then we did the model evaluation to understand the fracture propagation, the stress anisotropy, then also the stress shadow. Hydraulic fracture geometry. This is the illustration how the model looks like. This is the 3-stage hydraulic fracture model. We built using the AlChE simulation program. So with the model size 1400 feet for length, 1000 feet for width, and also height of 100 feet. And these three shows the stages with Bakken formation properties to illustrate for the properties of the formation itself. What parameters this is the list of parameters that we investigated. First is the formation properties, the Young modulus and Poisson ratio, the net pressure, which is the pressure difference between the pressure inside the frac, and also the minimum stress, which technically perpendicular to each other. The fracture length, the fracture spacing, and also the stress anisotropy in horizontal direction. I'll provide the simulation results. So for the formation properties, we did the Young modulus and also the Poisson ratio. The Young modulus shows in the left side. As we can see, when we change the Young modulus from 30, the green one, to 35, orange, and also 40, the blue one. As we can see, the results spread it out between this size up to this one. So we are talking about the stress shadow becomes this small up to this one, but it also changes the fracture total length. But when we play with the Poisson ratio, we change this Poisson ratio. When we play with 0.2, lays here, 0.25 lays here, 0.3, the result also lay here. So it means Poisson ratio doesn't affect the fracture geometry, while Young modulus affects more. What result we can conclude from this one? We can also track another result. We ignore the Poisson ratio and also the Young modulus. We assume that the relationship shows from this low one to the right one. We combine all the data. They are all in agreement that when we compare the y-axis, which is the stress shadow area, compare the fracture total length, which is the x-axis, we can see it has a linear relationship. So when you generate or propagate a longer fracture, it means you also generate a larger stress shadow area. What does it impact? That's what we're going to study for the next one. So after we come up with this result from the formation properties and also the fracture length, we made some assumptions that the fracture half length, because we want to investigate multiple parameters, we want to make sure that we only investigate one parameter in a time. That's why for the fracture half length, we contain that 1 to 280 feet for each model. So we do not change between one model to another one. And then for the shape of the stress shadow area, we simplified. We have its model as a rectangle. And then also there is no pressure gradient along the fracture. This is for the net pressure effect. So how about the net pressure effect? So if we can see here, this net pressure, let's say we have the fracture inside the pressure inside the fracture is less than the minimum stress after the propagation. So this is the stress shadow look like, the black box. When we get 0, the box becomes like this. When we increase the pressure inside the frac, it pushes the formation and also changes the stress around the fracture. When we increase and increase, let's say we try 3000 psi, how it looks, it becomes larger and larger. How can we determine the stress shadow area? By the change in the magnitude and also the change in direction of the stresses around the fracture. So we also did the stress anisotropy. The stress anisotropy is only in the horizontal direction, which is the difference between the minimum and also the maximum. And we use 4 stresses values and then we classify it as a high for 2400, medium for 1600, low for 900, and 0. It's like 83. We just call it as a 0 psi, a 0 stress anisotropy. So how it looks for the result, when we have the high and medium, this is the stress shadow look like. And also the medium, this is how it looks like. When we reduce, the stress anisotropy becomes lower and lower, and we have low, as we can see, the stress shadow area becomes larger compared to the high and medium. When you reduce becomes 0, it has the largest stress shadow area. What does it impact? Is it effect? Yes. This is, I show you the effect on the next fracture. We have the fracture spacing of 260 feet. So when we build the high, oh yeah, it's far enough. The stress shadow doesn't impact the next fracture propagation. For the medium, it does not really impact much, but it has the impact compared to the high. But when we become lower and lower, let's say we go to 0, as we can see, the fracture reorient and also contain because it grows shorter. So the stress shadow does impact the next fracture propagation. So how we overcome the stress shadow? We can play with the fracture spacing because we want to grow the fracture as long as possible, but we want to get the spacing optimum between one to another one. So this is the high stress anisotropy model. We play with 260, 200, 140, and 80 feet. When we have 260 feet, oh, it's far enough. We don't feel it. When we have 200 feet, it getting closer to the fracture, it has more impact compared to 260, but not much because as you can see, it can grow almost identical fracture with the same, almost the same length. When we get closer, smaller fracture spacing, 140, as we can see, the fracture gets impacted. It becomes shorter. How about if we get 80? Getting closer, it gets more contained because why? It can feel the most severe impact from the stress shadow from the first fracture. So the fracture spacing, we investigated the high, medium, low, and also 0 stress anisotropy. And for the fracture length of 280 that we kept, for each model, the optimum fracture spacing is 200 feet. For the medium, high, low, and also stress anisotropy. If we call it as a fracture spacing ratio, which is fracture spacing divided by the fracture half length, 200 divided by 280, the simulation suggests that 0.7 will give you the optimum number. So what are the conclusions we have? The stress shadow development is determined by the stress anisotropy, net pressure, and also fracture length. I just list the top 3 compared to other investigated parameters. And also we understand that the stress anisotropy not only influences the propagation length, but it's also the propagation direction of the hydrofracturing, because as you can see, when you have a low, it reorient. And the hydrofracture simulation results suggest that the fracture spacing ratio 0.7 generates the more identical hydraulic fractures. So if you want to improve, we need to further investigate also the effect to the production. So that's all my presentation. This is the acknowledgements for the SERC for funding this research, and also the EERC and SERC to permission to publish the work, and also Itasca for providing the exact license for the hydraulic fracture simulations. I think that's all my presentation. This is my contact info. In case you have any question or needs a further discussion, please feel free to contact me. Thank you.